Good morning, everyone. Today we are going to be looking at what we call number of solutions, or how many solutions you could have to any set of equations. Now, normally what we found is that I give you a set of equations, you do the work, probably neater than this, and you end up with one solution. And remember that this solution tells us that this is the point these two lines have in common, or this is that point of intersection that you find when you graph. It's the point that's on both lines. And I also know that were I to put this point into either one of these equations, it would end up with a true statement. So 4 times negative 10 plus 2 times 21 should actually equal 2. And negative 3 times negative 10 plus negative 2 times 21 should give me an answer of negative 12. Now, with this, it wouldn't make sense for this system to have more than one answer because there's only one point that works in both equations. So that's how I know that I only have one solution. But it turns out that's not always the case. So what other possibilities are there, and how will we know when we have more than, or perhaps less than, one solution? So let's just start by trying out this problem. 2x plus y is equal to 5 and 2x plus y is equal to 1. Now what I'm going to do is I'm going to go down to my graph because I know that normally I only have one solution because the lines intersect at exactly one place. So what happens with this one when I try to graph it? Well, don't forget that in order to graph it, a lot of times I like it in slope-intercept form. So I'm going to get the y by itself. I'm going to subtract 2x from both sides of this equation, and I'm going to do the same for this one. And let me just get those new equations down by my graph so you can see what I'm graphing. So here I end up with my rewritten system of equations. Y is equal to a negative 2x plus 5, and y is equal to a negative 2x plus 1. Some of you guys may have already figured out what's going to happen here. There's going to be a slight problem. But in case you haven't, don't worry about it. We will work it out here. So remember that this, for my first equation I'm graphing, is our intercept. That 5 is our intercept. And so that means that's where the line goes through the y-axis. And it's also my starting point. So I graph that, and this in front of my x is my m, or my slope, and it's saying how far up and over I go. Since this is really a negative 2 over 1, anything divided by 1 is just itself, it's saying I have a rise of negative 2 over a run of 1. So I'm going to go 2 down, 1, 2, and 1 over. And I'm going to keep doing that 1, 2, 1 over until I have my line. And my line is going to look something like this. Now, notice I am doing an approximation here because my graph is not perfect, but it gives me a pretty good idea as to what's happening with this line. So now that I've graphed my first one, let's graph the other equation. And again, I'm going to start with my intercept. My intercept is 1 here. And I'm going to do my rise over run, the number in front of x being my slope, and that's again a negative 2 over 1. So I'm going to drop 2 and go 1 over, drop 2 and go 1 over. So I end up with this pattern. And when I connect the dots, who knew that was going to be so useful to life, I end up with this line. Oh, well, that's a problem. Because here I had one solution over here. But when you look at this, how many points do these two lines have in common? Well, none. They never share a point. They don't come to some beautiful intersection because they're parallel. And parallel lines never intersect. So I could graph this forever and ever in both directions, and these two lines will never share a point. That means that when I'm trying to find the solution, I'm going to find out that there are no solutions. This is one of those problems in life that just does not have a solution. Now with this, I will always have this happen if I have lines that have the same slope. So anytime I have a line with the same slope, I'm assuming that they're going to intersect, and I find out that they do not. So you can see on a graph that in order to find that these two things are parallel or will not have a solution, you just need to have the same slope. But a couple weird things could happen algebraically that can show you that you will not have your solution. So let's go into one of those. Let's say I didn't graph this, because we know that graphing is not our favorite way to solve these. Let's say instead I tried to use linear combination or substitution. Both of them are going to look very alike. So if I tried to combine these linear combinations, I'd want to multiply one of these equations by -1. And I'm just going to do that with my first one. The reason why I want to multiply it by -1 again is I want one of my variables to cancel. So if I want to cancel out my x, I'd need this to be a -2x instead of positive. So I'm going to distribute that negative, and this is going to give me -2x plus -y is equal to a -5. And now I can add these two equations to find my solution. Well, 2x plus -2x is 0, plus y plus a -y, which is also 0, and 1 plus a -5, which is -4. 0 plus 0 is 0. -4 is still -4. Uh-oh. That's not good. Because when is 0 equal to -4? When is it the same time to have nothing and owe $4? It's not the same at all. These two things are entirely different numbers. So what we found is a false statement. If you ever find a false statement, so you've gotten rid of or eliminated all variables or no variables, but your answer is false, like 0 equals -4, or 1 equals 2, or 7 equals 9.5, well, that's just not true. It's false. So that means that if your solution didn't work, it means that your assumptions were wrong. So I assumed these two lines would share a point, and I was wrong. They don't. So that's what this means. Now you could do this with substitution too. You might get something else, like it might be like 0 is equal to +4 or 1 is equal to 2. Just the fact that it's not a true statement tells you that the lines are actually parallel and they will never intersect. So anytime you see this sort of situation, just say no solution. The lines are parallel. And that's what those little lines mean. Parallel. It's a shorthand for parallel. So let's look at the other situation then. I told you that there could be more than one solution. And that happens when we have these sorts of equations. So let's say I was going to graph this. First, I'm going to get y by itself. And I'm going to do that down at the bottom here, one equation at a time. So with my first equation, I started with a -x plus 2y is equal to a -2. I'm going to get y by itself by adding x to both sides. 2y is equal to x plus a -2. And then I'm going to divide both sides by 2 to get y is equal to 1/2, or half of 1x. X plus, well, -2 divided by 2 is a -1. So that'd be my first equation. Now to find my second equation, again, I'm just going to solve for y. So I have 3y plus a or 3x plus a -6y is equal to 6. Let me fix that. This should be an x on the top equation. And what I'm going to do here, subtract that 3x from both sides. I get -6y is equal to a -3y, or 3x plus 6. Divide both sides by -6, and I end up with y is equal to negative divided by negative is positive. 3 divided by 6 is 1/2, so a positive 1/2 x plus, well, 6 divided by -6 is -1. Okay, so let's look at our two equations then. You might notice something kind of odd. These are the exact same equations. In other words, these two things I started with are already equivalent. They're describing the same line, just using different numbers, because in the end I ended up with 1/2 x plus -1 is equal to y. And were I to graph both of them, well, I'd end up going through that -1, I'd do a rise of 1 and a run of 2, a rise of 1, run of 2, and I'd be getting this line here, with my first one. And of course, since my second one is the exact same equation, it's just going to lay exactly on top of this so that we get something like that for my second equation. And tell me, how many points do they have in common? Well, all of them is what I hope that you were thinking, or maybe even said out loud. All of these points are in common. That means that as this line goes on into infinity, every single one of those coordinates, this point, this point, this point, this point, all of those are solutions. So I don't have one solution where they intersect at one point. I don't have no solutions where they don't share any points because they're parallel. I have infinite, which is that sideways 8, infinite solutions because they share the same line. Now, of course, we don't graph everything. So how will this look with infinite solutions if I tried to solve it using a different method? Well, let's try to solve this one using substitution, just to change things up. So for my first equation, I'm going to get x by itself. And I'm going to do that by moving the 2y over to the other, or actually, you know what? Save myself some time. I already know what y equals. I know that y is equal to 1/2 x plus a -1. And I found that with the graph below. So instead of graphing this, I'm just going to substitute y into one of my equations. And let's just substitute it into this first one. So here, I know that -x plus 2 times my y value of 1/2 x plus -1 should equal -2 according to my first equation. Well, here, oh, I missed my 2. Well, here when I distribute my 2, I'm going to end up with -x plus 2 times 1/2 x, which is just x, plus -2 is equal to -2. When I combine my like terms, -x plus x is equal to 0. Which means I have 0 plus -2 is equal to -2. Well, 0 plus anything is just itself. So really what I have here is -2 is equal to -2. Well, that's great, but I'm trying to find my x value. And x has disappeared entirely. It's gone. So if x is gone and I'm left with a true statement, because let's face it, when is -2 equal to -2? Always. That's always true. Then that means that what we have here are same lines. We're assuming something where it's like, okay, these are two different lines, but that's not true. They are the exact same line. So if the variable disappears and you're left with a true statement, but not a very helpful statement, what it means is that there are infinite points of intersection because what you started with were the same lines. So here are 3 possibilities. You're either going to find a y equals and then be able to solve for x or xy. You're going to find a false statement with no variables, which means no solutions, or you're going to find a true statement with no variables, infinite solutions. So variables, 1 solution. No variables false, no solution. No variables true, infinite solutions. And you can do the same thing using only graphs to solve it as well. That's going to be it for today, and tomorrow we are going to practice this. So let's call it a day here. Have a great one. I will see you all tomorrow.